Good morning, friends. Today we are going to discuss the next part of this unit. In the last lecture, we talk about the electrophoresis, electroosmosis, streaming potential, and the sedimentation potential. Now we are going to discuss about the new concept that is a donor membrane equilibrium. Then what is the donor membrane equilibrium, how it arises, that we have to discuss in detail in this particular topic. Because as we seen that particular all these whatever the things are there, we have studied for this particular colloid, or say you can study it for the colloidal solution. It is simply called as a sols. Then what is the donor membrane? That particular whatever the or say donor membrane equilibrium, it is arises when the large diffusible ion, example the protein, is separated by the diffusion membrane from a diffusible salt. This donor membrane equilibrium is arises due to the large diffusible ion, example the protein, which is separated by a diffusion membrane from the diffusible salt. If here is shown that if a solution of the NaCl having the concentration C1 is separated by the membrane from the solution of a salt NaR of concentration C2, where R is a non-diffusible ion, at equilibrium it can be assumed that a certain amount of the X of sodium and chloride ions have passed through the membrane. This equilibrium can be represented as, you can see, initial concentration Na plus Cl minus C1 C1, Na plus R minus C1 C2 C2. After the equilibrium, Na plus Cl minus, that will become C1 minus X, C1 minus X, Na plus C2 plus X, and R minus Cl minus is equal to C2 into X. You can see the very much important thing is that how that particular donor membrane is developed or say arise. How it arises, that we have seen when, this is very much important, that line, when that particular large diffusible ions like the proteins is separated by the diffusion membrane from a diffusible salt. A large particular diffusible ion is separated through the diffusible membrane from the diffusible salt. Then and then only this donor membrane equilibrium is observed. Then the charge, that particularly the charge neutrality should apply to both the side of membrane. Therefore, the total concentration of the positive ions must be equal to the concentration of the negative ions on each side. Assuming that the solutions are dilute, the activities can be replaced by concentration. From the thermodynamics at equilibrium, mu NaCl2 1 is equal to mu NaCl2 twice. This is the equation number 1. But the chemical potential of any substance in terms of its activity can be represented as mu is equal to mu 0 RT ln A. This is the equation number 2. Therefore, equation 1 becomes mu 0 plus RT ln A NaCl1 is equal to mu 0 plus RT ln A NaCl twice. Therefore, A NaCl1 is equal to A NaCl twice, that is A NaCl is equal to activity of Na plus into activity of Cl minus. This equation number 4 becomes activity of Na plus into activity of Cl minus 1 is equal to activity of Na plus 2 into activity of Cl minus 2. 5. Equation number 5. For dilute solution, the ionic activities may be replaced by the corresponding concentration. Therefore, NaCl1 into Cl minus 1 is equal to Na plus concentration. There is a square bracket here to represent concentration will be nothing but a square bracket. Therefore, Na plus 1 is nothing but a C1 minus X, Cl minus is nothing but a C1 minus X is equal to Na plus is nothing but a C2 plus X into X, C2 plus X into X. It will give you the C1 minus X square is equal to C2 plus X in bracket into X. That is a C1 square minus twice C1 X plus X square is equal to C2 X plus X raised to, that is X square. That is therefore C1 square is equal to twice C1 X plus C2 X. Therefore C1 into C1 is equal to X in bracket C1 C2 plus twice C1. Therefore X upon C1 is equal to C1 upon C2 plus twice C1. This equation number 7, it is clear that the fraction X by C1 of NaCl which has diffused through the membrane at equilibrium depends on C2 depends on the C2. Therefore, the concentration of the sodium salt of protein. The fraction of the X upon Cm of the sodium chloride will be half only when C2 is equal to 0. But C2 does not equal to 0, therefore X upon C1 does not equal to half. Thus, the equal distribution of sodium chloride across the semi-permeable membrane cannot be attained in presence of the salt NaR containing a non-diffusible anion R minus. Very simple it is again. I will explain it again. See, donor membrane equilibrium that we have seen, how that donor membrane equilibrium attains. This will arise when the large diffusible ion like this particular protein is separated by a diffusion membrane from a diffusible salt. Then and then only this donor membrane equilibrium is possible. If this solution of NaCl of the concentration C1 is separated by the membrane from a solution of a salt NaR of the concentration C2, where R minus is a non-diffusible ion, at equilibrium it can be assumed that a certain amount of the X of sodium and the chloride ions have passed through the membrane. This is about the diagram. It clears all the picture whatever you have written. The charge neutrality should apply to both the side of the membrane. Therefore, the total concentration of the positive ion must be equal to the concentration of the negative ion on the each side. Assuming that the solutions are dilute, the activities can be replaced by the concentration. From this thermodynamic, at equilibrium mu NaCl1 is equal to mu NaCl twice. This is the equation number 1. But the chemical potential of any substance in terms of its activity can be represented as that we have mu is equal to mu 0 RT mu is equal to mu 0 plus RT This equation we have to remember. Then from equation 1 becomes mu 0 RT NaCl1 is equal to mu 0 RT NaCl twice. Therefore, NaCl1 is equal to NaCl2. That is the equation number 4. NaCl is equal to activity of Na plus into activity of Cl minus. Equation 4 becomes Na plus 1 into NaCl1 is equal to Na plus 2 into NaCl minus 2. For the dilute solution, the ionic activities may be replaced by the corresponding concentration. Instead of A, we can make there is a square bracket that will say the concentration. This concentration of Na plus 1 into Cl, concentration Cl minus is equal to concentration of Na plus twice into concentration of Cl minus. This is equation number 6. Now we can substitute concentration of Na plus 1 is C1 minus X, whereas Cl minus is again the C1 minus X. Na plus is the C2 plus X, whereas the Cl minus is the X. Therefore, C1 minus X square is equal to C2X plus into X. When you simplify all these equations, you will get X upon C1 is equal to C1 divided by C2 plus twice C1. From this particular equation, you can have the clear idea about the fraction X upon C1 of NaCl which has diffused through the membrane of equilibrium depends on C2, that is a concentration of sodium salt of protein. The fraction X by C1 of the sodium chloride will be half only when C2 is 0. C2 is 0. And it is impossible to have the C2 0. Therefore, the equal distribution of sodium chloride across the semi-permeable membrane cannot be obtained in presence of this particular salt in air containing a non-diffusible anion R minus. It is very simple concept. Again, you have to prepare this well. If you have any problem, you can ask freely. Okay, this is the last unit of this paper for this particular physical chemistry. Okay, please go through this each and every point. If you are not getting anything, you can ask me. What? Thank you. We'll stop here. Next part we will see in the next lecture.